Hello, everybody. Welcome to lecture. So today is the 6th Battlecode lecture. So if you've been following our previous lectures, Battlecode is all about incremental improvements. And we've been making various improvements to our lecture player bot, starting with some heuristics, going on to some pathfinding. And today we'll be focusing on communication. So we'll be thinking of ways to use this year's Battlecode's communication model to spruce up our lecture player bot. All right, so we'll get started by describing this year's communication model, which is just a shared array. So to be specific, you have a contiguous block of memory, and your robots are free to read from it and write from it. So the two ways your robots interact with this array is through this write shared array function, where you specify an index and a value and write to the array, and the read shared array function, where you specify an index and the function returns for you the value of the array at that index. So these are just the usual operations you can do with an array, but the key is that this array is shared amongst all of your robots. It is, however, not shared with the other team. Each team, the red team and the blue team, gets their own array. So this means that you don't have to worry about hiding your communications or obfuscating them because the other team can't read them. And it also means that you can't intercept the other team's communications. And just to put this communication model in the context of previous battle codes, I guess last year we had a flag communication system where robots had to be close to each other in order to communicate. The year before that, there was some sort of blockchain-based communication. So this year's communication model is comparatively simpler. A few years ago, we did have quite a few battle codes with a similar communication model. But one big difference this year is that our shared array has size only 64. So there are 64 integers that can be stored in your shared array. And just a little bit more about these methods and their bytecode costs. So the read shared array function is very cheap. So in comparison to your bytecode limits, which are usually on the order of a few thousand, you can do a lot of read shared arrays. You can probably loop over the array and do some computation there. Whereas writing to the shared array is comparatively a lot more expensive. You probably can't write through to like most of the array in a single turn without crippling your bot's bytecode usage. But it's still fairly cheap, allows you to write a reasonable number of times. So that's the situation for bytecode costs. And yeah, Aiden, do you have, so I'll be lecturing today with Aiden, if you want to say hi.
Hi, I'm Aiden.
Yeah, so do you have anything to add about the communication model?
Yeah, one thing I wanted to add is what you're actually writing and reading in this array. And every one of those 64 spots in the array contains a non-negative integer strictly less than 2 to the 16th. So that comes out to 60,000, about a little over 60,000 is your maximum map number, and the non-negative. And I believe they all start off as 0, right?
Yes, I believe that's right. So the array starts off at 0, and each cell contains a 16-bit unsigned integer, which means that its value can range from 0 to 2 to the power of 16 minus 1. All right, so we're going to jump straight in to making improvements to our lecture player. And in fact, I'd just like to, especially for those of you who've been, watching our previous lectures, do you have any ideas where communication might have been useful in the code we've written so far? This is a fairly powerful model of communication in that it's got nothing to do with the distance of your robots. You can communicate instantly. If you see something, you can immediately put it in the shared array. So how might we put this to use in our lecture player? Does anyone have any ideas? Like, what things did we do? There are a couple things I have in mind, like for our lecture player, which are kind of suspect, and would be perhaps a lot better if we use communication. Okay, so one thing I'm thinking of is our archons build strategy. So you may recall from the first lecture player lecture that our archon chose what unit to build based on the current count of that unit. So the archon had some minors variable, which kept track purportedly of how many minors exist, some other variable for the number of builders, and so on. And these are what it used to determine what to build. But the issue, because we have not integrated communication into any of our lecture player code so far, is that these numbers were actually not fully correct. These numbers were based just on how many units were built, like how many units have been built. But if a unit were to die, we wouldn't know. So for all we know, all our miners could have been decimated, and we still think that we built 50 miners, and therefore we shouldn't build another miner. So that is a minor problem. So how do we fix this? Well, with a shared array, the idea is fairly simple. It's that we want to actually maintain correct counters for how many of each of our units is alive. All right, so we want to use our shared array to have all of our robots interact with this shared array in such a way that we have correct counts of how many of each of our robots are still alive. Okay, so how might we do this? Well, with a shared array, it's fairly simple. So here's here's a first step at keeping track of proper correct counters of how many of each robot type exists. So the first thing we're going to do is, let's say you're a miner robot. We're going to associate each type. So we have 7 types in this year's game, 7 types of robots. We're going to associate each of them with a number. So we'll make a function. And also I should clarify, what we're doing this lecture is our explanation of the strategy will largely be slides-based and handwritten. But afterwards, we will have a working lecture player implementation that implements all of the ideas we discussed today, which we'll release. Okay, so suppose you're a miner unit. Basically we're going to have a function which takes a robot type and gives a number from 0 to 7. So the reason we're doing this is we have in mind, so our array is of size 64, and we're planning to use 7 slots of our array, which is not too much of it, to store how many miners there are, how many archons there are, and so on in each slot. So we have a function which gives us the mapping from a type to a position in this array. So that's the first thing we need. And now the idea for having correct counters is not to have any state. Don't care about how many miners you've ever built. Just calculate it properly at the beginning of each turn. So what your miner will do, let's say your miner happens to be associated with the 0th index. I'm just going to write some pseudocode here, so these aren't the actual methods provided to you. But what the miner could do is it could read the current value at your array. So this function here will say maybe there's a 7 here. So it reads that value, and it writes one more than that value to the array. So it writes to array 0, the value read of 0 plus 1. That's extremely simple. So the idea is that every one of your bots, so every one of your miners will run this function. Every miner runs this function. And that seems to basically lead to a correct counter implementation. But are there some details that I'm missing? Or are there fundamental flaws with this approach? If anyone has any thoughts, please feel free to put them in the chat. Will this work? Let's just have every miner write this function at the beginning of each turn, and sitting here we'll have the correct count. Well, there are a couple of issues here. When a miner dies, that's actually totally fine, because So this method of maintaining our counts is completely stateless. It doesn't depend on our previous turns. Okay, I see your point. Okay, so here's something that's actually a very good point. So here's something that we need to do. So right now, if all we do is have each of our robots run this, each one of our miners run this function at the beginning of each turn, this will not keep track of how many miners are currently alive, but the number of turns any one of our miners has ever experienced. So this number will be huge. It might overflow. So the first thing we really need to do is make sure that this number is reset to 0, reset all counts to 0 at the beginning of each turn. So that way, if a miner has died on a previous turn, it won't influence our counter. Okay, so does anyone have any further reservations about our current method? Like, are there more details that I'm missing? So remember our goal here. Our goal is to have some numbers for our Archon to use in its build strategy. And our plan is every turn, we're going to set all of these numbers to 0, and each robot, as it runs its code, is going to increment the slot corresponding to its type by 1. Okay, so why might this not lead to like a proper method of having a good Archon build strategy? What might we be missing? Or maybe this is just perfectly okay. Not sure. Well, what we might be missing here is, so let's go to the next slide here. So this is just a bit of a clearer depiction of what the plan is so far. So each of our robots corresponds to a slot. And here in like the correct code is what each robot is doing at the beginning of its turn. So this array ID is being obtained through this function type2index. Okay, what about the turn order of our different robots? Would the Archon read the array before all of the drives write everything? Yeah, that is exactly right. Yes, that is a huge issue. So first of all, there's an even worse issue that we happen to avoid, which is often when you're like, so like people care a lot about parallel algorithms, and often you worry about when two robots are writing to the same cell of the array at the same time, like who gets there first, what's going to happen. That's a big concern. But in Battlecode, all of our robots' codes are run sequentially. So at least we don't have to worry about like some sort of race condition at a array slot. Instead, this array number is going to increment up 1 by 1. But the issue is that the Archon is not necessarily the last robot that goes. So the Archon might read the array at a point in time where these counts are still in progress. So suppose that Archon is the first robot to run. Then all that we'll see in the array is 0, 0, 0, 0, 0, 0, 0, assuming we've done this whole resetting business correctly, which we also need to think about. But that's the issue. The issue is your Archon will see in progress counts. Okay, so how do we fix this? Does anyone have any ideas how we might fix this? How can we have some like good, robust, correct numbers for our Archon to base its build strategy on? Well, if we try and use the current numbers for Archon, like the number of each robot's alive on the current turn, it would be difficult to use these counts because, as you've said, it's in progress, and there's no clear way, or if any way at all, for the Archon to be able to access all of those numbers when some robots haven't even had their turn yet. So here is the idea. We're going to remember the counts from the previous round as well. So previously we were using 7 slots of our array. Let's use a few more slots and go up to 14. So now our data arrangement looks like this. We're going to have 7 slots for our previous round and 7 slots for current round. So these counts here, these numbers here, are going to be in progress. So these are the numbers that your robots will be modifying as soon as they get their turn. Whereas the previous round counts are going to be saved from the calculations of the previous round, and these are going to be what's used by our Archon or any other robot that cares about counts. Okay, so this is used for our logic. Okay, so now we're nearly there. So just roughly speaking, we need to be, so now if we look at our indices, now we have something like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So for our robots that are doing an in-progress count, they'd want to look at 7 plus like that type number that we had. They'd want to look at this position of our array and increment it by 1 using that same code here. And for our Archon or any other robot that cares about counts, it would omit this 7. So it would look at just the type ID. So this is great. So if we have this set up, we're in a very good position, but there's still a little trick that we need to use to actually get this previous round and current round business to work properly. That we need to discuss. And the other thing we still need to discuss is how we're going to ensure that our current round is zeroed out at the beginning of the turn. Okay. So here is what I propose for our final data layout. Okay, so we have 7 slots for our previous round, and we have 7 slots for this round. And now, if you look at these code snippets in the bottom right, this explains how we're going to cycle through, how we're going to save our data from the previous round. So let's think about it for a second. So let's focus on this round counts, and let's say we build them up over a round. So we build them up, and eventually we have the counts of all of our robots sitting here. If we keep the previous round, if we use the indexing from the previous slide, where the previous round was the first half and the current round was the second half, what we need to do at the end of a round is move all of these numbers here to the previous round section, which is all right, I guess. We copy over 7 numbers, but how does a robot know that it's the last robot in the turn? It gets a bit messy. So instead, what we might want to do instead is keep these numbers here. And then the next time, the next round, we remember that now these 7 are going to be our previous round data. And let's use these 7, which we don't care about anymore, for this round's data. So the idea is that we're going to constantly swap previous round and this round, like in this cyclic fashion. And a really cute way of doing this in code is using modular arithmetic. So previously I had, so this num types variable here is 7. And previously for this round, I had this guy always be 1, and previous round always be 0. Instead, we're going to be constantly cycling around these 1s and 0s using modular arithmetic. So this mod2 symbol just says, what is the remainder of your round number when you divide by 2? So it's basically 1 if the round number is odd, and 0 if the round number is even. And it's the opposite for previous round. So the effect here is that you're going to constantly cycle this round and previous round. So this is the final formula for how a robot determines where to write. So if your robot's updating the in-progress counts, it uses this expression for this round. If your robot's is looking at the previously stored values to do some build logic, it's going to look at this. It's going to use this expression for previous round to figure out the array ID to look at, the array index. Okay, does anyone have any questions about what I've done so far? All right, so there's just one last detail to tackle here, which is how are we going to ensure that all of our values are zeroed out at the beginning of each round. So what we need is a robot should be able to tell. A robot should be able to tell if it's the first robot to run in that turn. So how might a robot be able to tell this? So on the first robot to run in this round, how might you ensure that your robots know when they're the first robot to run? Because then they've got to do a bit of extra work. They've got to make sure these in progress counts are zeroed out. So the hint is this one last array index that are value in our array that I've tacked on to this data arrangement. I've put it at the beginning at index 0. So that's why this round and previous round variables have a +1. And this value is the current round number. So in Battlecode, you have access to the current round number. We're using it in this logic as well. So the idea is to actually store this round number in your array. So every robot stores, whenever they run, they just put their round number into here. So when all of your robots run the third round, they'll all write 3 into this array. Like so, it won't do anything after the first robot writes a 3 into that slot. What variable is numtypes here? So numtypes is just a constant that we actually define at the top of our code. And so it's just a number of different types in Battlecode, which this year is 7. So the reason we need this number is because if we have 7 values here, then, and this happens to be and we want to access like the second half of the array, then this arithmetic gives us 1 times 7 plus the type ID plus 1. So this shifts it over by 7. So we're looking at the second copy of the array, of the counter array. So it's a constant. So it doesn't change. Okay, so any other questions? Okay, so going back to round number. So on round 3, all of your robots access the round number. They see it's 3, and the first robot is going to write this into the array. Write this to slot 0. And when it does so, it's going to realize, since it's the first robot that runs, that hey, currently sitting in that slot is not a number 3, but a number 2. Because no robot has yet experienced the wonders of round 3. No one has written 3 onto that slot. So this is the first, this robot knows that this is the first robot on round 3. So we can implement the check. We can check if RC.get round number. We can check if it's equal or if it's not equal. I hope that's right. I don't think there's a second equal sign. I'm not sure. We hope that it's, we check whether it's not equal to what's currently in slot 0. Sorry for the weird code, but again, everything should be, all of the code will be available on Lecture Player. So we check this condition, and if not, we update the round number, and we also loop through this entire array and zero out everything. So that completes our method of counting round numbers. So it looks like we're now properly transitioning between rounds. So before I go to a demo, does anyone have any questions about this? All right, so in that case, I will now show a demo of Lecture Player implementing the logic we just showed, maintaining robot counts. So like here. Okay. So it's our new Lecture Player. So using the new code that will be released after lecture, playing against the example funds player. So and also one more thing I've done is every robot, I'm using its indicator string to report the count as we've stored it. So it looks into the previous round data and reports that count. So that way we'll be able to check in the client whether our counts are working or not. So let's just play the game. All right, so it's been a few turns. Our archons have spawned a few robots. And now if we click on our miner, we see that its indicator string is set to 5, and that is indeed the correct count as told to us by the client. We can click on our soldier's indicator string is 3, and its count is 3. So we managed to do it using 15 slots of our share array. We're able to now maintain correct robot counts. So Archon, they're printing the number of Archons, but they can also access all of these other numbers from the shared array, the number of soldiers, the number of miners, and they can now use that for their build strategy. And indeed, they do use it for their build strategy. So that's it for robot counts.
Okay, I'm going to be taking over for a bit to show a few more things we can do with the shared array. And so let's just think about some other things we could do with it, because with the current implementation of robot counts, it's only ever going to take up 15 of our 64 slots. So we have plenty of room for other things. And one thing that comes to mind is locations. And that's like a very broad category. So you could have the locations of your archons. You could have the location of enemies. You could have the location of resources. And there's so many things you could use with this locations for. So now we have to think about, how do you store a location in this? So if we have our map and we have, let's say, oops, sorry about that. We have our map. And if we have our archons in these spots, these archons don't know where each other are. And that'll make it hard to coordinate anything between them. So one way to solve this problem is to store each of their locations in an array. So right now, each of them has a map location. So all of them have a map location where they are, and that map location has an X and a Y. So the first way we could think about doing this to show a location, so giving a smaller example so we can put some actual numbers with it, is we could do the X and the Y for every point we want to mark. So for example, we have a yellow dot, and then we show the yellow dot is at 0, 1, just like that's its coordinates. And this will work fine. The biggest downside is it takes 2 indices for each location. So with this, let's say you took your whole array just to store locations, you could show 32 locations because it would take 2 of your integers for each location. So there's a pretty quick, better solution we can do, which is facilitated by the fact that our maps are never bigger than 60 by 60. Does anyone have any ideas what this would be? Yeah. So what's similar to what someone said, but I'm not going to explain it in a little bit of a different way, is because the map only goes up to 60 by 60, we can wrap our numbers and come up with a different location indexing scheme. So instead of having, for example, this location here be 2, 2, we can just have it be 8. And with this, that just halved the number of locations in our array we need to use for the number of spots in our array we need to use for our locations, which is pretty nice. But there's still a better solution, and this one's a little bit of a strange change from a other solution, all I've done is added 1 to every single number here. And it might be hard to immediately see why that would be helpful. It doesn't effectively change anything as we're using it, but it just seems like it's an unnecessary complication. But why this is useful is because it allows us to reserve 0 to represent an unused spot in your array. So let's say, for example, you are using Gorov's counting scheme he gave earlier, which uses up like the first 15 spots in your array. So then you have all the rest of it, all the other 49 spots. And you don't know, and let's say you're using them to just represent things. In this case, let's just say every single one would just be an enemy. You're trying to keep track of all the enemies. So the first time a robot sees something, sees an enemy, it will go find a spot and put that location. Let's say it says, oh, enemy at 5, and then one says enemy at 6. And then since this array is initialized to all zeros, the rest of it is going to all be zeros. And the problem with our old strategy here is, let's say you see an enemy at 0. You go and set a location to 0. You think that's still an unused spot. So you haven't changed anything. You've just made a 0 into a 0, and you still think that's an unused spot in your array. So that's why we just use a 1 for that instead. And a 1 would represent this position here. So another thing that we can talk about is, how do we get these numbers? You can see they do wrap like in this fashion, and then it goes around here and does it again. And then it goes around and does it again. And to help explain that, we're going to use some modular arithmetic again. Or the modular arithmetic will come in later in the process. But at first, it's very simple. All we have to do is multiply. So in this case, we have a 3 by 3 grid. And we can just take our x coordinate and we can add to it 3 times our y. And then we add 1 for the reason I explained before. And now we get this current setup we have. And then one thing you'll notice is in our actual maps, it's not going to be 3, but 3 is just going to be the width of the map. So now we can look at some code and talk this through a little bit more. So here we are implementing this thing we just talked about, which is converting locations to integers to store in our array and undoing that. So if we look at location to int, we first check to see if that location is null and return 0, because we're using 0 as a location to represent a null spot in our array. And otherwise, we return 1 times the x, 1 plus the x plus the y times the width. And that's what we store in our array. And then when we're undoing this by converting back to locations, we first see if our number is 0. And if it is, we return null, because that means it's an unused spot in the array. Otherwise, we're decreasing our number by 1. That's what this minus minus does, just to remove this plus 1 we added up here. And now we use modular arithmetic, which basically cuts off anything bigger than the width of the map. So if we went over here and we had like a 5, it would just push it down to the bottom row, and we would get, or this would be a 4 actually, with a 5. Oh, sorry, yeah, it would be a 4 and going on this one, and it would just push it down to 1. And then if we had a 6, it would push it down to 0. That's all doing this percentage sign width does. And then for the y, we just divide it by the width. And if you took like 5 divided by 3, you would think like that's no longer an integer. So in Java, the division is between two integers assumes you're doing the floor of that. So 5 divided by 3 in this case would equal 1, which works because you can see we have a 5 here. I've written over it a little bit, but 5 there corresponds to 1 on the y-axis. Anyone have any questions about this part of it? Okay, Gob, do you want to go
Yeah,
over
sure.
keeping track of enemies?
Am I screen sharing properly? Okay. Right. Okay. So yeah, so now that Aiden's covered storing locations, that gives us the ability to think about how we might apply this to Battlecode. In particular, as Aiden said, we might want to store locations of resources, of enemies, and so on. And it's great to put these in our shared array because if one of your robots sees a resource or an enemy, your entire team immediately knows. Okay, so today we'll be focusing on applying this to storing enemy locations. So our goal is to store enemy locations in our shared array. So what might we want to do? We want to be able, if we are a scout robot, maybe we're a soldier that's just venturing into enemy territory and we find their base, we're going to want to report this. So we're going to want a function, provide a function for reporting an enemy. Okay, so this is one function we want to report. And what this is going to do is some way, somehow, it's going to store the information in our shared array. What else might we want to do? We might also, so great that we can report enemies, but if we don't act on that information, it's not helpful. So something else we might want to do is get the closest enemy. Okay, so we've somehow stored all of these locations in our array. And now this will just give us, it's pretty self-explanatory. It's going to give us the location of our closest enemy. And finally, something that you might not think about is the following. If you report an enemy location and then that enemy wanders off elsewhere, you don't necessarily want that location to still be taking up space in your array. One, it's taking up space and need limited space. And secondly, because maybe if that array is still, if that location is still around, it might be returned by a get closest enemy call, and you might venture over there only to find that there's nothing. So finally, we need to be careful about clearing obsolete enemy locations from our array. This is the third function we're going to focus on. And with these functions, the hope is for us to have a pretty powerful attacking scheme. We'll have robots roaming around. They can just report an enemy and say your soldiers at any point in time can use this get closest enemy function and head in the direction using the pathfinding described in previous lectures. So this looks very enticing. And how do we do this? Okay. So, okay, and there's one more thing to think of. So sort of gave it away, but let's think about the arrangement of our array. So we decided we're going to use the first 15 slots for counters. That leaves 49 slots for enemy locations. So even if we're clearing our obsolete enemy locations and have only the correct enemy locations, it is going to be difficult to store all locations in these 49 slots. Okay, so the way we're going to be encoding these enemy locations is using the technique that Aiden described. So each location will be an integer using the location to int function, but that integer can still be pretty large. So we're basically going to have to put each integer into its own slot, or maybe 2 integers per slot. But this is a far cry from the total number of possible enemy locations, which might be like 3,600. So you might have a situation where you have lots of, let's say, blue team is your enemy, you're the red team. You have a bunch of enemies, maybe all clustered here. And you also have enemies elsewhere. Maybe there's some miners here that you wanna be able to take out. But this cluster here ends up just taking up your entire array space. Okay. And if we think about it, we're using these enemy locations to figure out where to go. And do we really need to store two adjacent locations in separate slots in our array? So this is the idea of keeping track only of approximate enemy locations. So if we see a location at any one of these blue dots here, we're just going to remember that this square has a length much larger than 1. Maybe it's a 10 by 10 square. We're going to remember that this square is something we might want to visit. And this significantly reduces the number of possible locations. So hopefully we should now be able to cover this cluster here, cover this cluster, cover this unit here, cover this unit here, and have space for all of these in our array. So now a soldier wandering over here will know that this is its closest enemy, head there. Our soldiers over here may, sorry, these are meant to be red soldiers. Yeah, so this will help us represent much more different enemy locations on the map and help our soldiers attack. So this is one nice idea. Okay, and how we're going to store these enemy locations is as a list. So we have these 49 slots here, and Aidan sort of already described how this works. We're going to put a list of locations. So these are numbers which correspond to positions on a 2D grid. And we're going to have a list of these numbers taking up the remainder of our array. So this will be our array of enemy locations, a list of enemy locations. And this list will have no particular ordering. We're just going to shove it in. So you can already see that maybe to find the get closest enemy, we're actually going to have to do a search over this entire array, a for loop. But that shouldn't take too much bytecode. And the key motivation for storing it this way, as opposed to maybe another way of storing it would be to have a slot for each location. And then you can immediately just look at the location and see there's an enemy there. We're not storing it that way because that would require a prohibitive amount of space. We only have a limited amount. This is a much more flexible solution that doesn't seem to lose us much. So that's what we're going to roll with. Okay, so let's think about the report enemy function now. Okay, so here is its signature. So all you basically get in is an enemy map location. So we're trying to maintain this array. What do we need to do? Do we need a for loop? Do we need to look at something? Do we need to add something? Does anyone have any ideas how we're going to implement this report enemy function? So, basically what we want to do is add our location to the array. But there are a few conditions under which we would not actually want to add the location. So especially keeping in mind this approximate business that I just described. So can anyone think of what conditions might prevent under what conditions maybe not want to add a location to the array if our soldier reports an enemy, say? Well, what if we already have stored this blue location in our array, and then we see another enemy over here? Then this is a situation I just described, where you have multiple enemy locations clustered together, and it doesn't really serve much use to put them in different, both of them into the array. So what we're going to do is check that it's not part of an existing cluster. So these squares here I'm calling clusters. What we're basically doing is clustering the enemy locations. And the second condition is if there is an empty slot. So it may be the case that despite our efforts, our enemy location array has filled up, in which case, that's life. We just can't add it to our array. So this is the logic we're going to use. And this is how our data arrangement ultimately looks for our array. So our enemy locations are just going to go from left to right here. And specifically, we're adding our location to what's more appropriately called a list, and we'll just add it to the end. So add it to like the first empty slot we see. So that's what we're going to do. Okay. Now let's think about clearing obsolete enemies. So again, since for clearing obsolete enemies, we don't have like a new location. Like it's only a function of a robot controller. And what it's going to do is iterate through our array. Okay. And does anyone have any ideas what condition we might check to see if a location is now obsolete? This might be a bit trickier. So remember, we want to delete a location if we no longer believe that there's an enemy there. Sense robots there. That's an excellent idea. Yeah. So first of all, there's one thing to check, which is, so this is again, each of our robot runs its own copy of the code. So if there's a location in the array, which is, on the other side of the map, there could be an enemy there. There could not be an enemy there, but our robot has no jurisdiction over that. It's just not going to touch it. So first, yeah, our robot should be it should be in our robot's vision units. And second, yes, as was said in the chat, we're going to run sense robot and the location. And if there is no enemy in that location, then we're going to delete that location. Okay, so this seems like a reasonable scheme. Can anyone think of any drawbacks to this scheme? Like, is it possible that we'll delete a location when we really shouldn't have? So let's think about what happens if our robot has moved just like one square to the right. Yeah, nearby locations have enemies. Yeah, that's sort of right. So like if your robot has moved just like one place to the right of our location, do we really want to delete that location? So it's a bit complicated that we ultimately don't want to. Like this cluster still has robots. But what we can do is run this clear obsolete enemies function before we run all our report enemy functions. So that way, even if we delete the location of a robot, we'll re-add it. So that's okay if we have a situation like this, where maybe this is our vision radius. This is a cluster of robots, and the blue robot has moved, say, here. That's fine. We'll delete the cluster and like re-add a new cluster, like maybe this one. That's fine. But there's another condition. There's another case, which is what if this robot has moved just slightly outside of your vision radius? That's a problem, because now we're going to delete that robot, and maybe there are no other red robots in the vicinity. So now your team no longer knows that this robot is nearby. So we haven't actually handled this in our code. This is an issue. Like in Battlecode, you have heuristics. It's not always perfect, but maybe you might find that adding more conditions to this will give you a stronger robot. Maybe you only want to make a decision when you're confident, like maybe when you're dealing with clusters that are so within your vision radius that they're entirely contained. So maybe you might want more conditions for this clear obsolete enemies function, but that is how we've run it in the code and the heuristic that we've come up with. So does anyone have any questions about this clear obsolete enemies function?
I had one thing I wanted to add about what you were just saying about how we can just remove the cluster and add a new one. And that's what we're doing right now, and it works fine, especially because our robots don't use that much bytecode right now. But if you're running into bytecode limitations, if you remember, writing is a lot more expensive than reading. And you can see in the example Gaurav drew, he's moving a cluster like one square, which involves a write and costs a lot more than not doing anything to that cluster. So that's another thing you could think about.
Yeah, that makes sense. Okay, so I guess the get closest enemies function is now, it's fairly simple. We're going to just loop over all of our enemy locations, look at all the distances to our current location, and find the shortest location. So with just this logic, a soldier's now able to just query which direction should it head off into to run into enemies, which is a really powerful thing. And we can see just how powerful it is by taking a look at our new lecture player in action. So let's do it first.
While he sets this up, I want to mention one other trick we did, which is part of why this works so well in the example he's going to show, which is when the game starts, we set a few robot, like enemy locations. So we set an enemy location just to the opposite corner or to all the other corners opposite of where the Archon that's running this code is. And what that does is we just assume there's an enemy there, which makes our first soldiers go and check that place out before doing anything. Like, because at the beginning of the game, you don't know where any enemies are. So this way we just give it somewhere to start so it doesn't just wander around until it finds one.
Yeah, it's extremely powerful.
You'll see here that the soldiers start going immediately towards the enemies, even without knowing the enemies are there, just by assuming that.
Okay, so our lecture player is in blue, and it is, it's just making quick work of example fence player. And yeah, a lot of this is to do with that the soldiers improve pathing. Yeah, even on this very large map, the soldiers are able to find all of the Archons and sweep through the map. Okay, so that concludes all of the improvements to lecture player's code that we're making for today. And just a final comment, which is that, and after this, we're going to be talking about bit hacks, which are, something that you can apply in your own code. But just a final comment about bot improvements, which is that the point of this lecture is to give you, a set of improvements you can make to your bot. It's to give you like a platform. Like, we haven't necessarily chosen the optimal heuristics, because that would sort of defeat the point of Battlecode. Rather, if you look at the code, you'll be able to see, some very cute, clever ideas that can be used to make your bot better. And the idea is for you to go, with this knowledge and improve your bot in other ways. For example, we've handled enemy locations. What if we did similar things for resources? And so it gives you a platform for improving your bot, and Battlecode is all about incremental improvements. So yeah, that's it. All right, so now do we want to move on to bit hacks here?
Yeah, so bit hacks is a technique which we've kind of already done without explaining what we've been doing. Another thing is, I know we've got to an hour, so this is a little bit like bonus info that we will mention in the next lecture, but I think it's very useful, so feel free to hang around. So bit hacks, basically, you may have heard Gaurav mention we could store multiple ints in a slot in our array, and that's kind of contradictory to what we were saying before. First thing we were saying was that we could only have one integer in each slot in our array. And how that works is surprisingly simple. In fact, we already did it when we were handling locations. So we took an X and a Y and just combined them into, we were doing X plus width times Y, and then we would throw that into one of our integers because we knew it would fit. And basically what we're doing here is a sort of bit hack, just explained in seen in a different way that we're going to be looking at them later. So here what we're doing is we just take an X and make it the smaller part of a number. So our X is always going to be less than width, just because of how the grid works. And then we have a Y, which is always going to be a multiple of width. So once you take this final number, you can take everything that's less than width, that's the X, and then everything left over once you remove the X is Y times width. And so we're going to get into this a little more. And a lot of this has to do with binary. That's why it's called bit hacks, and how these numbers are actually stored inside the computer. So one thing to note is these numbers are strictly less than to the 16th, which is 65536. So a maximum number is 65535. And if you look at this 2 to the 16th as a binary number, this gives us 16 bits. So you can see I have written out 16 ones there. I'm going to give a brief introduction to some binary, but this might be hard to understand if you've never seen it before. But basically how it works is instead of every digit going up to 10, so like we could not have a 9 in this slot, it can only be a 0 or a 1. And then instead of going past 1, you just go to the next spot over. So then you would have another 0 or 1. And if you think about with a normal number, if you have like 320, you got your ones place, your tens place, your hundreds place. In binary, if you have like 101, you've got your ones place, your twos place, and then your fours place. And this continues by multiples of 2, which is why 16 bits gives us 2 to the 16th. So you'll see here, if you take your 16 bits and set them all to 1, you get 65535, which you'll remember is our maximum value in our array, or maximum value for these integers. And then another interesting thing is if you take all of these bits, shift them over, and then just put a 0 in on the left, you get 2 to the 15th because so you got like your ones, your twos, your fours, and you're taking off 1 power of 2. And 2 to the 15th minus 1, which comes from the fact that it's sort of because of it's starting at 0. And what's interesting about this is you'll see that when we shift it over by 1 bit to the right, it decreases by about half. And what that is not just about half, that's not how it actually works, but it's dividing by 2 and then just cutting off the remainder. Because if you think about this last 1 here, it goes into a bit that does not exist and is just cut off. So this would be going into the halves spot, but we aren't keeping track of that, so it's just lost.
Yeah,
So-
another way to
Right.
think about why it's like 2 to the 15 minus 1 is if you added 1 to that number, like the same rules of addition apply for binary, then like you'd have carry and all of those ones and they'd all flip to zeros and you'd have a 1 in the 2 to 15th place.
Yeah,
that's-
so if you added a 1 here, this would have to become a 0, and then you'd add a 1 here, and this would become a 0, and so on until you end up with a 1 at the next spot over and all zeros. Which, thank you for that. Seems like a good explanation. So now we're going to see how we can use this to actually fit more numbers into our 16 bits. So there's a lot of ways we can split up our 16 bits. We could turn it into 2 8-bit numbers. 2 to the 8th is 256. So we can do 2. So 2 to the 8th minus 1 is 255. So we could get 2 numbers from 0 to 255. We could also do 4 numbers from 0 to 15, 8 numbers from 0 to 3, or 16 booleans, so 16 zeros or ones, which is then, that's obvious why that works because it's going right back to our definition here. And then sometimes what's even more useful is you can also break it up unevenly. So you could do 1 boolean and 1 number less than 2 to the 15th minus 1, which this is a really nice way of doing stuff because this is a quite large number. For example, a location could easily fit in this number, and then you have this leftover information you could store. So maybe you want to mark what that location is. In fact, the locations, since they only go up, maps only go up to 60 by 60, which is 3600, you can fit that in 12 of your bits. And 2 to the 12th is 4096. So this easily fits in there, and that leaves you with the last 4 bits for whatever you want. So one way you could use this is you could store a location and then use this last 4 bits, which could give a number or a series of like binary flags of giving information about that, could tell you what that location is storing. So maybe like if this first one is a 1, it's friendly, and if the first one's a 0, it's an enemy, and so on. You could have come up with some sort of scheme like that. But now we're going to go on to the logic of how you actually handle breaking up these bits. So here I just drew how you could break down the middle and get 8 bits on this side, 8 bits on this side, and break it up into these two numbers. So here's some code that does this, but I'm actually going to do this in reverse and first show why it works and then go back to the code. So let's say we got a number 51 and we got a number 129. You notice those are both less than 256, which means you can fit them in 8 bits. So I got the binary value of 51 here, which is 110011. And then I also have 129 here, which is 100000001. And you can see I can just put my 51 into the first half of our array, just drop it in here and put, or not into an array, but of a series of bits. And then this whole series of bits goes into one spot in our array. And then I can just put a 129 into the other half. And you'll see this creates a new binary number, which in this case is equal to 13158. And that is sort of meaningless to us, but it does fit within a number strictly less than 2 to the 16th. So we can store this value in our array. And now we can look at how we extract our 51 and our 129 back out of this. So we take our final value here and we shift it 8 bits to the right. That's what this is, a shift, a right shift. So you can see we take our number here, this one, and we just push it this way. So we push it this way a lot and we lose everything on this side. This is all gone and this is our new number. So there's our number. And you'll remember, because we put 51 on the left side of our series of bits, now all that's left is 51. And since the rest of it is zeros, that does not change our value at all. So this number here is equal to 51 as a whole. Oh, sorry, 51. And now what you can do, because you know that your upper half of your list is 51, you can move this back up here and then subtract it from your original binary array, and then just take the lower half. And that's going to be your 129, because remember we put 129 onto the lower half. And there's actually better ways of doing this than shifting it back up and subtracting, but we'll maybe get into those in the next lecture. So now we're going to look at the code. We're doing the same thing again. Our example was counting sages and laboratories. And one thing to note is that since these have to be strictly less than 256, which will probably be true, you're probably not going to get more than 256 of either of those. This should work fine. But in the case it does, one thing you could do is you could just clamp your number to be less than 256, so that if you somehow ended up with 300 laboratories, your array will just say you have 256. But most of the time, depending on what you're doing with them, most of the time you don't actually care. You just know you have plenty of laboratories. You don't need to make any more. In this case, you could just bring it as high as you can go without overflowing into where we're storing sages. So now here's the code for writing these two integers into one slot in our array. Right now we're just using index 0 because it makes it easier. So that's where those two zeros come from. We take sages, we shift it 8 bits to the left, which, as you can see down here, we have our sages on one side, this 51 here, and shifting it to the left like that turns it into this number because it just fills everything to the right of it with zeros. And then we add laboratories to it, which is all we have to do this. Just add that one onto the same number and it'll add to that side over there. So now we have, in our array, we have 13,185, 5 in our array. And now we can read that, and then value here would equal that 13,185. So you could read this at a later time in a different robot, and then we're going to see how we can re-extract these two values out of it. So the same thing I explained before, we can get our sages just by cutting off the 8 bits to the right of a large number. So we just cut these off to get our sages here. And then we just subtract that from here, from the front half of our array, to then get our laboratories. And that's basically it. There's a lot more to this and a lot better ways to implement it than this code, but I thought this was one of the more readable ways to do it that we will hopefully explain in the next lecture. Did I miss anything, Gaurav?
No, I think that's a very good explanation. All right, so I guess that is basically it for today's lecture. So we gave improvements based on communication for lecture player, both for storing counts of robots and for keeping track of enemy players. So the new code is now on the lecture player repo, but keep in mind that if you're taking this class for credit and you're looking to beat the reference player, you're going to have to take these techniques and improve them. Try and use the same ideas in different ways for different goals in Battlecode in order to get a better bot. But yeah, hopefully this gives you a much better platform to do so. And yeah, the code is now in the lecture player repo, which is in the Battlecode organization and is public. So thank you very much.